This video on torsion module, it's lecture 9 on module theory. The torsion module is important because for the structure theorem of abelian group or structure theorem of module over PID, we need the concept of torsion module and torsion free module and the torsion part of a module. So we'll go through on that one by one. First, torsion and torsion free module. What is torsion and torsion module first? So what is torsion module? By the way, what is the torsion element of a module? The torsion element of a module is, so let M be a module and X is a element of M, and this is called torsion element. Torsion element. So it's a torsion element if there exists some number in some element in ring, that ring. Obviously, a not equal to 0, otherwise Ax equal to 0, but a not equal to 0, but Ax equal to 0. So a not equal to 0 and Ax equal to 0. Then X is called torsion element. So 0 is a torsion element of the module, obviously, for any A. Now, what is torsion module? A module is called torsion module if every element is a torsion element. So if every element is a torsion element. So every element is torsion. Is torsion module. Every element is torsion module. Now, what is torsion free module? Torsion free module is just the opposite. It's not the negation of this, it's just the opposite. So every element other than non-zero is not a torsion. So there is no non-zero torsion element. Non-zero torsion element. 0 is always a torsion element, but no other element in the module other than 0. So non-zero element are there is no such non-zero torsion module, torsion element. So every element is torsion, here no element is torsion other than 0. Now it may happen that some elements other than 0, some are torsion and some are not torsion. So then we talk about the torsion part of the module. So what is the torsion part of the module? The set of all torsion element. Set of all torsion element is called torsion part of the module. So sometimes it's write M suffix T. So M suffix T is the torsion. Now, obviously, if it's a torsion free module, for torsion free module, this MT is equal to 0. And here MT is just a whole M. Now, there is an example of torsion module, torsion free module, but which may not be free. It is torsion free means it is every element is other than 0 is not torsion. But free means it is the basis. So there is different concept. So we have an example. We'll give an example where a module is torsion free but not free. So example is take the ring as Z, and this module as the Q, rational number with addition, usual addition. So it is a torsion free. Why it is torsion free? Because every element other than 0, it can't be you add up to this because your ring is Z. So if you take any element from the Z and if you take any element from the X other than 0, so your Nx is 0 if and only if your X is 0. Oh, one more, A is not equal to 0, so N is not equal to 0. So in non-zero element of ring, and you take an element from M, and Nx is 0 if and only if that X is 0, because N is not equal to 0. So 0 is the only torsion element. So it is torsion free. Now this is not free. Why it is not free? Because any two element cannot be independent. So any two element, if you take two element X equal to P by Q, obviously Q not equal to 0. And you take Y, which is some R by S, S not equal to 0. Then your Qx plus minus S into Y is equal to 0. So this is it can't be independent, independent. So any two element of non-zero element, obviously if it is a zero element, will also dependent. So any two element cannot be independent. So if it is a free module, then it's a basis. A basis must have just only one element. So if it is free, then the basis has a single element. So it is cyclic then. So but Q is not cyclic since ring is Z. So if you take, say, Q is generated by the element X. Now you can't generate X by 2 from X. So how do you write X by 2 in terms of X? So it can't be any nx for all n belongs to Z. For all n belongs to Z, or take X not equal to 0. Obviously other X not equal to 0, because if X equal to 0, then Q equal to 0, contradiction. So there is a contradiction. So there is a module which is not which is torsion free but not free. So now there is an important result on that. For any module M over commutative integral domain, some book take integral domain as commutative, some book do not take. So we write commutative, whatever it is. Integral domain take as a commutativity or not. We take in this result the commutative ring, the integral domain as a commutative ring. Then the quotient module, this is torsion free. This is the basic idea. Is this if MT is a set of all torsion element? So if we kill that element, if you identify the all element of this torsion element in the module as with 0, then obviously that after identification that M mod MT is a torsion free, other than that 0 element. So but we have to prove rigorously. What is the proof? The proof is the outline is this. So let M is a torsion free element. So M is a torsion free non-zero element. Torsion free non-zero. So let M be a torsion free non-zero and generated by sorry, we have to just take no, we don't take torsion free. It may be anything. That module may be anything, may not be torsion free. So you first take any element on X bar, say X plus MT. So what is M mod M quotient MT? Is a set of all quotients like X plus MT, the set of all quotient where X belongs to M. Now take that as a torsion element. Let this is a torsion element. So let X bar is a torsion element of M quotient MT. So what is this? That means there is a non-zero element in R such that Ax bar is equal to 0. Now what is Ax bar equal to 0 means? Ax bar equal to 0 means it is just Ax bar equal to empty. 0 null element in M mod MT is 0 empty. So what is this? This is nothing but Ax belongs to MT. Ax belongs to MT. So since Ax belongs to MT, that means that Ax is a torsion element of. If I take X bar as a torsion element of M mod MT, then we have for some A non-zero, Ax is a torsion element of M. Now, since M is a torsion element of M, there exists some B not equal to 0 in R again in that ring, so that B into Ax is equal to 0 for some B, non-zero B. And what is this? So BA into X plus, but B not equal to 0, A not equal to 0, therefore BA not equal to 0, because it is integral domain. Since it is integral domain, B not equal to 0, A not equal to 0 implies BA or AB not equal to 0. So BA not equal to 0, and we have this BA X equal to 0. So X is a torsion element. So X belongs to MT. So every element of this is so if you take a torsion element in X mod empty, then X is empty. That means X bar is actually empty. X bar is empty, which is actually 0 in this. So 0 is the only element. So take any element of this M mod empty, which is torsion, that implies that that element is 0. So every non-zero element is not torsion. So that means this is a torsion. We prove it. So next, one more important theorem is this: a finitely generated torsion-free module over PID is free. This is very important. We know any finitely generated torsion, we finitely generated module over PID is finitely generated, but finitely generated torsion-free module over PID is free. So how do you get this idea? The idea is this: say take M is a torsion-free element, non-zero module. M is torsion-free module. Other than 0, if you take a module as a 0, then it is torsion free. It's interesting that if you take the module as a just trivial module, set only 0 element contains 0, then it is torsion free because there is no other element other than 0. So every non-zero element is torsion free, not torsion. So it is a, you have to take non-trivial case that M not equal to 0, because if M equal to 0, then it is a free. M is free. So we take M not equal to 0 and is torsion free. So any element other than 0 is not torsion. Now take it is a, since it is a finitely generated, we take a set which is generate X M. So that set is say X1 X2 Xn, and X1 X2 Xn generate M. Now we can realize this thing, and we can say that there is a subset of that X, X1 X2 Xm. M is less than or equal to N. So that this is linearly independent. So we can take the linear independent part in first. We just reordered, and we can take that. Say if element like that, the first element is A, the second element is a 2A. We replace that second part to the last thing. So if we say A, 2A, then B and 2B or 3B, we reordered that A, B, 2A, 2B. So AB is a linearly independent, but A and 2A is not linearly independent. So take all the linearly independent vectors or elements of module in fast. So you just reorder, and we have a linearly independent maximal. This is maximal. So you can't have more than that. So that no more than M element is linearly independent. Remember, this X1, X2, Xn is a generating set, may not be basis. So now this is will be a basis since it is a maximal independent subset. Now let F equal to that span B, span of B. Now that no, that may not be basis actually. We take the linear maximum linear independent set. Say we can take say A 2A, B 2B. We can take AB, or we can take 2A B. If you take 2A and then B, then A, then 2B, then 2A and B may not be basis because 2A cannot generate A. So it may not be basis. So we just take the spanning set of B is F. The span of B is F. Now M is non-zero torsion free. That means M must be greater than or equal to 1. At least one element must be there. Now we consider for each I, for all I, we consider some scalar. There exists some scalar AI as well as there exists some scalar Aij, and not all 0. Some may be 0, not all 0, such that AI xi plus sum over j equal to 1 to m Aij xj is equal to 0. So this is true because this x1, x2, xn are the maximal linearly independent set. So if you take any one more element, other than x1, x2, xm, that will be linearly independent, and we can write that not all 0. Now ai not equal to 0, because if ai equal to 0, then that part, this summation aij xj is 0, and since all aij not equal to 0, that actually implies that x1, x2, xm are dependent, but we assume that it's a maximal independent set, so ai cannot be 0. Now for every xi, we take that ai's and we put a equal to a1, a2 dot 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 dot, a1 into a2 into dot an. So all ai is not equal to 0, therefore a not equal to 0. Since remember this is our PID, so it is an integral domain, so that element not equal to 0. Now what happened? Then since f is span of this x1, x2, xm, that means ai xi is just minus of that, so it is minus of this thing. So linear combination of some aij xj which belongs to f, because f is the span of that x1, x2, xn. So this is true for all I. So what happened? So right, so AIXI is belongs to F. So your A1x1, A2x2 all in X, A2x2 all in X, A and Xn all in F. Now consider say A1 F1 and you multiply it by say A2 A3 dot 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 AN A1x1, this also in F, because F is a spanning set of B. But remember this is a PID, so it is a commutative ring, so you can just take that as a A1, A2, A3, and A1, you can just write this as a A1, A2, A3 dot dot, you can just using that commutativity in ring A2, A3 dot dot AN, A1 is equal to A1, A2, A3 dot dot AN. That means AX, this is X1, AX1 is belongs to F, so for all, this is true for all I, so AXI belongs to F for all I. What is the meaning of that? So xi, x1, x2, xn, that is a generator of M. So that means your A into M is a subset of F. So x1, x2, xn are in M and that generates M. That means A into x1, A into x2, or A into xn generate A into M. So, but each element are in the subset element of F. So A into M is a subset of F. Now we consider this map. We consider this map that F from M to F. We consider the projection map such that x goes to Ax. Now this is the linear map and this is the injective map. Since M is torsion free, so since it is torsion free, it is injective. Why it is injective? Take Ax equal to Bx, that implies A minus Bx equal to 0, but x is not equal to 0. This is true. If it x equal to 0, okay, we have to prove Ax equal to 0, Ax equal to Bx. If X equal to Bx, then we have to show that A equal to B. But if x equal to 0, what happens? X equal to 0, 0 goes to 0, 0 goes to 0, and other than what, why is the, it's a monomorphic injective? Why A minus B equal to 0 now? So A equal to B, it is torsion free, M is a torsion free module, so if X is not equal to 0, then Ax equal to Bx implies, no, what we have to take, sorry, we have to take not Ax equal to Bx, so we have to take Ax equal to Ay, right, sorry, so A is the fixed element, so we are taking two input x and y, so Ax equal to Ay, we have to be x equal to y, Okay, so A is not equal to 0, so x minus y equal to 0, because x minus y is a torsion. It can't be non-zero because the module is torsion free. So if x minus y is non-zero, then x minus y is torsion free. So A into x minus y cannot be 0. So since A, remember, A not equal to 0 and M is torsion free. So since M is torsion free, any non-zero element of the module and non-zero element of the ring cannot be multiplied gives to 0. That means x equal to y. So it is a monomorphism, injective. So it is a monomorphism, are linear. So what happened? So it is a monomorphism are linear. That means since it is a monomorphism, f is isomorphic to f of m. The range is isomorphic to the domain because the kernel is 0. So by first isomorphism theorem, that fm, that range of f mod kernel of f, that isomorphic to m. But now this kernel is injective, so kernel is 0. So m is isomorphic to fm. But what is fm? Fm is submodule of, no, fm is a submodule of, no, this fm is a submodule of f. It is not only subset, it's submodule. The submodule of f, because any range is a submodule of the codomain. But f is free. Now f is free because f is a submodule of m. Now, any submodule of m is free. Any submodule of free module is so no. Why f is free? Yes, because f is no, f is free because of f is a span of B. So there is a basis. B is the basis of f. X1 x2 xn. So it is a linearly independent maximum. Whatever is linearly independent, that spanning set is a spanning set. So B is the spanning set of f, and this spanning set is linearly independent. That means B forms a basis of f. So f is free. Now we know that submodule of free module is free. So fm is free. So fm is free because we know in the previous video that if f is any free submodule over R, any ring, then and f is m is a submodule of f, then that is free. So fm is free. So fm is free. But m is isomorphic to fm, that means m is free. M is free. So this completes the proof. Next theorem is also important thing, that a finitely generated module over PID is direct sum of its torsion part and a free module. So it is like M is a direct sum of this. We have to find that free part of free submodule FT, MF. We know what is MT. So M is given. Now proof is like that. Take B hat is xi plus mt set of all coset. This is in quotient module, xi in M, and take for I 1 up to n. Now this is a basis. We know this is the basis of this that quotient module. This is the basis. So because f mod mt is a free module, in the previous theorem it is a free module. So this is the basis, and that take that basis as a xi plus mt is the basis of this. Is a finite dimensional. We assume this is a finite dimensional, finitely generated. So since f is finitely generated, that m mod mt is finitely generated. Now take the corresponding B in M, x1, x2, xn. That's set. And what happened with this B set? Now this is linearly independent. This is linearly independent because xi plus mt is linearly independent. You can check it that these are linearly independent. Check P is linearly independent. Since xi plus mt is linearly independent, so these xi's are also linearly independent. Now take that set as a generating set and take span of that B is Fm. We will show that that if MF work actually, that MF and MT direct sum will be M. So two things we have to show that every element of M can be written as MT plus MF, element of MT and plus element of MF. That means the sum, and that is direct. So to show this is direct, we have to show that intersection of MT and MF is just only zero element. So we have to show two things. Now, MT is a torsion module. MT is torsion module because every element of MT is torsion. We collect all these torsion element of M. So it is the MT is a torsion module. So if since MT is a torsion module, so intersection MT intersection MF is the null, only zero element. Because the element of FM, MF cannot be a torsion element other than the zero element. Cannot be torsion. Because that xi plus mt is torsion free. Remember that xi plus mt is torsion, that m mod mt is torsion free. So you already proved that m mod mt is torsion free. That means xi plus mt cannot be a torsion element. So any element of mf other than 0 cannot be torsion. So the intersection is 0. So we have the if this the sum of mt is direct, actually the sum of mt plus mf, this is actually direct. So we have to show that that is m, that is equal to m. So you have to prove that that is equal to m. So how do you prove that is equal to m? So we take a mapping, we have a R linear map from m to m mod mt. This is the canonical natural canonical map. Natural map. What is the natural map? X goes to x plus mt. This is natural canonical map. Now eta of x in any x belongs to m, we can write this as an element of m mod mt, and this has a basis xi plus mt. That means this is written as I equal to 1 to n ai into, for some ai in real in ring, ai plus mt. So because xi plus mt is the set of basis, this forms a basis, so that every element of that m mod mt can be written in this form. So linear combination of the basis element. Now this is unique. This representation is unique because this is a basis. Since it is a basis, therefore it is a linearly independent. So this representation is unique. This is for some AIs are unique. Now we consider this eta. This thing you have to consider this eta of x minus that part, that summation ai xi I equal to 1 to n. Whatever this is actually eta of x minus that. So this is 0. This is actually mt, and mt is 0 in the m mod mt. Remember, mt is a 0 element of m mod mt. So this is 0. Now, take y as that element, x minus that summation I equal to 1 to n ai xi, and that is eta of that is 0. So that means it is in mt. 0 means here so this is empty, this is No, this is not equal to 0. This eta of this equal to 0. So this is actually in the kernel. So this is actually in the kernel of eta, because eta of that y is 0. So this is kernel, but kernel of eta is empty, because in natural map we know that in the natural map kernel of eta is empty. So this is empty actually. So y belongs to empty, m suffix t. So once y belongs to m suffix t, what happened? That means your x minus this is just empty. So x equal to actually summation y plus summation of just y equal to x minus that. So x equal to y plus that somewhere I equal to 1 to n ai xi plus y. So we got this thing. So we have this this summation part, which is actually in mf, m suffix s, and that y part, y is actually in empty. So we have this any element x in M can be written as a linear combination of xi's, which belongs to mf, is the free module, plus a torsion part y. That you got this y using this kernel thing. So this completes the proof. The average finally generated module over PID is the direct sum of torsion part, each torsion part, and another free module, and that free module will be generated by x1 x2 xn. And how this x1 x2 we get this x1 x2 xn? We got this x1 x2 xn from the basis of m mod mt, because m mod mt is torsion, and that completes the proof. So we stop this video here, and next from next video we go into the chain module, chain condition of modules of Artinian or Noetherian ring.